to hearing your talk.
It's hopefully intelligible for people who don't normally do quantum computing. That's the goal.
Patricia, you want to go ahead with the introduction? We're already live.
Right.
Sorry, Richard, what were you saying?
Oh, I was just saying I'm looking forward to Lex's talk.
All right. Okay.
Hopefully I'll be able to understand it.
You'll get it.
All right. Okay. Please, Crisia, do the honors.
All right. So good afternoon, everyone. Be welcome to this week's Quantum Matter seminar with Lex Kemper from North Carolina State University, who is going to tell us how to engineer quantum circuits to examine thermodynamics and topological aspects. Thank you very much, Lex. Feel free to start.
Okay. So yeah, Adrian, thank you both for the very kind invitation. I'm excited to be here and tell you, well, be here virtually, right? And tell you all a little bit about what we've been doing, working at the intersection of condensed matter physics and quantum computing. So my name is Lex Kemper. I work at NC State University. And yeah, here we go. The first thing I should do, if at any point you all have questions, I don't know how you normally do it. I'm happy to answer them mid-talk. I'm happy to answer them after talk. I don't have a chat window, but maybe Adrian or Crisia can keep an eye on it for me. Okay, thank you. First thing I should do is thank my collaborators. I've done a lot of this work together with Jim Friedrichs and Sonia Gajori, who are at Georgetown and IonQ. Locally at NC State, my graduate student Akil, who is there, and Xiao, my postdoc, who there's another picture. And we have some experiments together with the team at University of Maryland, particularly in a group of Norbert Linke reviews. They've been kind enough to help us with some of the quantum computing experiments. Okay. Why do we do this? Right? Why should you care about quantum computing when you are, say, a condensed matter physicist? This is the quantum matter seminar, right? So why is this a thing that you should care about, or why is it interesting? Well, so let me give you sort of my perspective. So if you go to my group website, you'll find this picture that I cooked up. We do quantum materials in and out of equilibrium. And this is, and quantum materials out of equilibrium is something that I've been doing for some time. Now, experimentally, the way you do this is you have to go to one of these things, right? This is the LINAC coherent light source that sits at Stanford, where you do experiments where you take materials and you drive them out of equilibrium, and then you make some measurements. So pictorially, what you should expect is, you have some laser that comes in that excites your material, and then you have some other laser that, in this case, ejects some electrons, and then you measure them. And then as a function of time difference between the red laser and the blue laser, you look at what your photo emission looks like. And so in that way, stroboscopically, you build up a picture of what this material does when you drive it out of equilibrium. So you go from a photo emission spectrum that looks something like this to something that is animated, right? And so in there, you can see oscillations, you can see dynamics of population, you can see all sorts of things, and then you can spend whole PhD careers analyzing this, figuring out what's going on. Now, from a theorist perspective, right? What do I do with this? Well, I go and I use really big computers to try and say something sensible about this. So on the left, on the top are two of the big supercomputers that are available in the US. One is Corey, named after Gertie Corey, the first American woman to win a Nobel Prize. And on the right is, that one's at NERSC. On the right is Summit, which is named after a mountain, I guess, at Oak Ridge. And using these, you can do all sorts of numerical calculations that you care about as a condensed matter physicist. So at the bottom, I have 3 examples that are coming from my area of physics, sort of time domain physics. On the left is some calculations we did using non-equilibrium Green's functions to look at the dynamics of population in various materials. In the middle is a result from one of our hosts, actually. This is one of Adrian's results on time domain DMRG, looking at a spin chain, if I'm not mistaken. And on the right-hand side is some work with Steve Johnston, where we've looked at, how an excitation in a particular correlated model diffuses. So these are great, and these take advantage of all the high-performance computing techniques and all the other things. but eventually they all reach a barrier. In the case of exact diagonalization, my Hilbert space eventually gets too big to fit on either of the computers or more. In case of DMRG, it has that problem, but also it's got dimensionality issues. And in the case of the non-equilibrium Green's functions, I also run out of memory. I can't do these things anymore. So eventually we all reach a computational barrier, and then we have to do something. And we can, of course, improve our numerical techniques. But one of the alternatives to this is to try and use quantum computers. Now, if you're new to anything like mine, they're kind of all over the place these days, right? Like I open my phone and I find 50 new quantum computing things. IBM and Google have big superconducting ones. IonQ, which is now a public company, has trapped ions that vaguely look like this. Microsoft was working on topological quantum computing. They still kind of are. And these days, we also have a photonic one. And so this is a new tool, right? It's a new kind of thing that I could potentially use to solve my problems in condensed matter physics when my classical techniques have run up against a wall. All right, so this is why you might want to care, and this is why we're sort of thinking about how can we use these to solve our problems moving forward. So a little bit about how these work. I'm not going to bore you with very many of the standard things, but the basic idea is that you, instead of bits, you have qubits. Those can form superpositions, and those have nice, their vectors have full 2 to the n storage length for n qubits. And that's great for information storage because I can store all of them at the same time in superposition. You can use this to solve classical computer algorithms faster than you otherwise could. Schur's algorithm, which is a search algorithm, maxcut, which is about slicing a graph. I'm not going to talk about any of those things because we're going to talk about physics today. All right. So how do you deal with these things? How do you program them? How do you try and get them to answer your physics? So classical computers use gates, right? And you can tell that this has been around for a while because this picture has been copied 50,000 times, so it's a little fuzzy. That was a joke. It was kind of silly. Right, but you build these together with gates. So you have NAND gates, and with that you can form universal gates, and you can build whatever it is that you want. Quantum computers are similar. They also have circuits. They look like this, and I'll sort of read you through how we read these things. They're read like music from left to right. Each line is a qubit. They always start in the 0 position. And what you do is you track through your wave function as you go through these various gates. So the first one you have is you have just a tensor product of 0 and 0. These are 2 qubits. They're not entangled. They're just by themselves. The first thing that we go through is this gate here. It's called a Hadamard gate. And what that does is it changes my 0 qubits into 0 plus 1. Everything has to be normalized, so I have 1 over square root of 2, but that's all it does. So if I go from 0 cross 0 to 0 cross 0 plus 1 cross 0. So that one was very straightforward, and these just, are rotations on my Bloch sphere. Here I've rotated by a particular angle, but really I can rotate whatever angle I want. This is just a simple example. This is an interesting one. This is called a controlled knot. So just like here in classical land, I can have a NOT gate that inverts my qubit. This is a controlled knot. And what it does is this one is 0, do nothing. If this one is 1, flip this one. Okay, so I have a 0, 0, so that should stay where it is. And I have a 1, 0, which because this is 1, this will change to a 1. And so in the end, I will have a 1, 1. And this is how you read them. Now you make them more and more complicated, but this is the basic sort of idea. What you'll notice, or maybe not, is at this point, I don't have a state that factorizes anymore, right? I have a Bell state. I have a nice entangled state. This is one of my 4 Bell states. All right, so these are also entangling gates if you apply them. And this is where, now I can use the power of quantum computing and all of the entanglements and all these other things, because now I've pulled them together into one object rather than 2. Okay. So this is the straightforward sort of, here's how you read these things, and here's how you manipulate the wave functions. And what could we do with that? As condensed matter physicists, one of the things that we often think about is we care, so how do we use this as a quantum simulator, right? We care about correlation function. So we care about if I have some macroscopic quantum state or if I have some any-body wave function. Given that I have some observable B at R prime and T prime, what is the probability that I see, or the amplitude that I see A at R and T? This represents a whole host of our observables, right? Just to name a couple, I could do connectivity this way, single particle spectra work this way, neutron scattering, these all can be written in this form. And so this is a thing that I might care about when I'm looking at some kind of condensed matter system. Now, the way we would evaluate this is you go to your many-body textbook, whatever your favorite was, and you find that you do this through Lehmann representation. Right, so I take a wave function, I apply an operator UA that represents my A. At time evolved to T, I apply B, and then I close this expectation value. And then I can fill in complete states into it. From the quantum computing perspective, we're going to do the exact same thing. We're going to prepare a wave function, apply an operator, time evolve, apply another operator. And this is what that would look like. Slightly more complicated than what I just showed you, but it connects to all the pieces that you know. My qubits always start in 0, so I have to prepare whatever phi is, whatever state I've chosen to prepare, right? That's this part. I apply my UA operator, I do time evolution, and then I apply my B operator. Now, the reason I have this bit on top, this is an extra qubit, we often call this an ancilla for ancillary, is that if I just do this, I will end up with a wave function that just has a phase attached to it. And phases cannot lead to they cannot lead to observables. And so what I have to do is I have to somehow produce an interference pattern. And the way that's done is by making this, this 0 + 1 state, and then applying this only on the 1, and then doing the interference at the end. Yes, Richard.
In your initial expectation value for CFT there, is that phi naught, or it's a general wave function?
It's just phi. It's whatever state that you've prepared that you're going to measure the correlation function on. Oh, sorry. Yeah, sorry, you're right. These should both be phi naught. Thank you. It should be the same, right?
Thanks.
Okay. So to give you an idea of sort of, how this works, let's try this out on a system. I'm going to try this for the periodic Heisenberg model. This is very well known. It's got a ground state. It is positive where all my spins are all pointing up. My one excitation that I can make is just a single spin flip. That's a high energy state. And we know that, in fact, the first excited state are composed of magnons, right? These are these nice little rotating tops with a dispersion that goes roughly like this. This is a very well-known system. And so this is a nice test bed to sort of try this on. And the first thing I'm going to do is try this on a simple two-site model, right? So for two-site Heisenberg, we know that we have the singlet and the triplet. So what I'll do is I'll start in the ferromagnetic state and then measure, say, the XX, the spin X correlation function. So here's what you get. So I'm taking up, I'm flipping one of them down, I'm doing a time evolution, and I'm flipping it back, just like you would classically. You can do this either on-site or nearest neighbor because it's two sites, but for either one, there's only one frequency in your problem. It's the difference in energy between your singlet and your triplet, and there it is. There's the real part, there's the imaginary part. And the dots are what you get if you run this algorithm on a quantum computer 3 years ago, 2-3 years ago. So precisely the thing that the circuit that I showed you, you implement that, and this is what you get. Yes, Masoud.
What's the platform? What platform? What kind of quantum?
Sorry. So this is, thank you. This is one of the IBM superconducting quantum computers. And I forget exactly which one this was on. Probably Toronto. It's not around anymore.
So it's qubits, flux qubits, or
flux qubits. Yes. Good. So we got this and very happy, I'm down to, we thought, okay, great, let's try this for 4 sites, right? That's a little bit more like a Heisenberg model, a little bit more like a chain. I don't just have singlets and triplets. So here are the curves for what you should get for the on-site delta x = 1, delta x = 2 correlation functions. And here's what you get from the quantum computer. It is not great, right? This is not what you would like if you're trying to do some kind of calculation and trying to go beyond what we have available with classical computers, right? Because this is 4 sites. It's a Hilbert space of 2 to the 4. It's not large. I could do this on a Casio watch probably if I tried hard enough, right? It's not so good. But, you know, you can still kind of see patterns in this. So we soldiered on a little bit, and we tried what is now very common in quantum computing is a bunch of error mitigation strategies, right? And this is one of the things that you'll find if you attend quantum computing talks. They will tell you about what sort of error mitigation they did to take into account, you know, these results are wrong, I threw them away. I know that there's this particular error in my quantum computer, so I fixed this up. So we did a few of those. 2 of them are straightforward. The last one is not really an error mitigation and more like I know there are only 4 frequencies in my data. So let me try and do a Fourier fit. If you do all that, you get something that is a little bit better. Here, the red curve is what you should get. The blue curve is just readout correction and the blue curve is readout in phase and scale, and the yellow one is using a Fourier fit. So this looks a little bit better. And in fact, if you just take a Fourier transform, you can already see that this is not too bad. I at least have the correct frequencies in my data. They leak over into different momentum channels because of various reasons, but at least, you know, the correct frequencies are in my data. So the reason I'm telling you all this is in part because one of the things to keep in mind is that these days we are very much having to deal with what can I do on a quantum computer to a point where I still get a reasonable signal out of it. On a lot of hardware for things you would like to do, you're just not going to get anything. The signal is going to be too weak, or you're going to have dephasing, or you're going to have something that ruins your experience. And so the game in part is to figure out ways that you can measure things that are still useful even today, and with the aim of going forward to where we have, you know, proper ones. And so those are the sort of 2 things we're doing. We're trying to figure out how to do something useful today, and we're building sort of the infrastructure for being able to do calculations that we really care about at some point in the future. Okay. Good. Okay, this looks much better because it's just fit. All right, so they're promising tools, but you need to be taking care of noisiness in the NISQ era. And in case you've seen this word, NISQ, it stands for noisy intermediate scale quantum. So intermediate scale meaning I have somewhere between 4 and 40 qubits. Okay. Any questions at this point?
I have a question.
Please.
Yeah, this is just a basic question.
Mm-hmm.
So you showed us schematically how one would go about to implement the scheme, right, with these propagators. But if you start from a given Hamiltonian, how do you write down those blocks that you show there?
This is a hard problem.
Okay.
That is so let me see if I have a good slide for this. So what you do is you would build it out of 2x2 blocks, because on a quantum computer, you only have 2-qubit operations available. You would do some kind of Crowder decomposition, and given that you know sort of a 2-site Hamiltonian, you can build the exponential of each 2-site piece in this manner. This is not at all intuitive or obvious or anything about it. And in fact, there's a whole how to construct time evolution operators or unitaries is a whole research field on its own. And so when I say it's a complicated question, it's because it is.
Okay.
It took us some time to figure this one out. Now we have sort of a standard 2x2 building block, and now we can build from there. But in no sense do we know that this is the best one or anything else like that.
Okay, thank you.
Mm-hmm. But these days, actually, some of the software will do it for you, so you don't have to do it by hand.
So
That was a good question.
Now, Lex, you're starting here from simple product state, but if you wanted to start from the ground state of an antiferromagnet, it would be a lot more complicated, right? So
Well, the thing,
how would you do that?
If you want to start from the ground state of an antiferromagnet, right, then what you would do in this piece is you would have to prepare that. So you would have to either know in advance which quantum operations to do, or you would have to optimize variationally, given like I want to minimize the energy, and then you need to do some of these algorithms like variational quantum eigensolver. And that's a whole nother thing by itself. So preparing the ground state is also a hard problem.
Gotcha.
These are all really good questions. These are all the kinds of questions that, when we first started, we had the same sort of like, how do you even do this? Okay. So the two things I wanted to tell you about today are, I was going to talk about how you do thermodynamics on a quantum computer, in particular using something called partition function zeros. This is not just useful on quantum computers, it's also useful on classical computers. And the second thing is, how do we start looking at some topological aspects of models using quantum computers? And so these are the things I'm going to talk about today. These are the archive links on the bottom here that correspond to that. Okay. So what you find in both cases is you find phase transitions, right? In sort of classical thermodynamics, you have things like melting, and on topological phases, and I'll talk a little bit more about that, start to have topological phase transitions without any observables. They're both phase transitions, although very different ones. And so we have to treat these both very differently. And so we'll start with thermodynamics and looking at sort of classical phase transitions. So when we think phase transitions, right, this is what we teach our students. We can take, for example, an Ising model. So that if all I have is available as a control parameter is temperature, then at low temperature, it may form a ferromagnet. There'll be some point, an ice point or a melting point, and beyond that, it'll form some kind of disordered state. We can apply a magnetic field and we can get a little bit more control. We can have magnetic phases in two different directions. The way we think about this, right, is we think about the free energy. So on this side of the phase diagram, my energy wins. And on this side, I have a lot of entropy. And so on this side at high temperatures, my entropy wins. So the way you compute these things is you compute the energy. That's fairly straightforward. Whether I have a wave function or whether I have a mixed state, the energy is just, an operator you can evaluate on a wave function. The entropy is harder because I have to get a density matrix. And so far, when I've told you about quantum computing, I haven't said anything about density matrices or mixed states, right? Like everything was nice, pure states. So how do we get those? Well, for density matrices, right, it's just the equivalent language. I can do this for pure states also. Pure states live on the surface of a Bloch sphere. The mixed states are mixtures of these convex mixtures, and they live in between. They live in the middle somewhere. I can make these as many pure state I want by tracing out part of the pure state. So there's various dilation theorems, Stein spring dilation among them, that says that you can do this. You can always take some mixed states and embed it in a larger pure states. So let me give you an example of how this works. We're going to bring in our simple Bell state again. There it is. The corresponding density matrix for this state, right? I flip this around and take the outer products is this. I have 0, 0, 0, 0, 1, 1, 1, 1, and the cross terms. And now to get a mixed state from this, what I do is I trace out one of them. So here, there's no conventional notation for this. So this is what we use. So I'll trace out the first qubit. So that means I pick up this term because 0 matches 0. I'll pick up this term because 1 matches 1. I won't pick up this one, nor that one. And so my density matrix is this one is the fully mixed state. So this is how you can represent these things on a quantum computer. Even though it works with wave functions, if you trace out part of your state properly, you end up with a mixed state. And ideally the one that you want. Now for a thermal state, right, we know what the density matrix should look like. It's an outer product of all of my individual eigenstates weighted by whatever their energy is, all divided by the partition function, which just makes sure that the trace is normalized. So how can we make such a state? It turns out there's a useful construction for this. It's not by no means the only one, called thermofield double states. They have applications in black hole physics and all sorts of things I don't know about. But what you do is you construct this thing. You take two copies of your state, of your system, A and B. You produce them in identical eigenstates. You weight them by what the energy is divided by the square root of partition function. And it's sort of two lines to show that if you trace out one of these, what you end up with is the correct density matrix that you want. This was nicely theoretically predicted by a group of Femsier and implemented in a group of Chris Monroe. They used a trapped ion quantum computer. They built this complicated quantum circuit and then traced out one of them. And in the end, what you had was a thermal density matrix. So this is a thing that we know how to do. Okay, good. So now I have my density matrix, right? I should be able to continue with my program. I should be able to take the energy, which is trace rho h. I should be able to take the entropy, which is rho log rho, right? That's what we wanted. That's what we were after. But it's still on my quantum computer, right? And I cannot take a log on a quantum computer. Every operation has to be unitary, so I have to do something else. And what you have to do is you have to measure it. And to do that, you have to do tomography. So you have to take each element of your density matrix and measure it. This is a bad idea. This is a bad idea because it requires 4 to the n, roughly, measurements for you to make. And the whole idea of doing quantum computing is that you go beyond sort of these exponential scalings. And this is not a thing that you want to be doing because of, 4 qubits, 4 to the 4 is already 64 measurements. If I start to think about 10, this becomes rapidly undoable. So this is not what you want either. So we need to think of a different approach to try and get at the free energy if I want to study phase transitions. The approach that we're going to use, or that we used, is instead to go through the partition function. Previously, I talked about this just as a normalization constant, but it's got more in it, right? If I take, for example, a one-dimensional Ising model, and I look at what the partition function is as a function of inverse temperature and field. This is my phase diagram. That's what the partition function looks like. It's got some small value here. It's got big values out here. That doesn't look too interesting by itself, but we know free energies involve logs of these things or derivatives of these things. And so if you plot the log, you can already start to see a lot more structure, right? And these are things that we sort of know as physicists, right? We know that you get thermodynamic observables from either logarithms or derivatives of the free energy. So that we know that there's a lot of information contained in this particular function. But I'm going to think about it in a different way. I'm going to think about it as just a function, a real valued function on the set of parameters of the Hamiltonian. So H is it in Ising model, for example, applied fields?
Can I ask a question?
Yeah, please.
No, I just wanted to, maybe I missed it, but how do you measure the partition function again?
I haven't gotten there yet.
Oh, okay, never mind.
I will tell you.
Thanks.
Okay. Thank you for the question. It's a very good question. We will get to how we measure this precisely. All right, so we're going to think about this as a function. As long as the number of states is not infinite, this is a nice function, right? It's a sum of exponentials. There are no divergences. There is no anything. It's infinitely differentiable. All of these things are nice, right? Just a sum on states weighted. That means I can do a polynomial expansion, right? And I also know from algebra that every polynomial is characterized by zeros. I also know that the partition function, as we normally think of it, doesn't have any zeros. It's a sum on exponentials, right? So it doesn't have any of these, which means that it has to have zeros because it has a polynomial expansion, and that means the zeros must lie in a complex domain somewhere, right? In the algebraic sense, I've got for example, a quadratic like this, it has zeros, they're just complex. So what we're going to do is work backwards and think about this partition function as a function in a complex plane. That means I need to make either beta or h complex. We're going to talk about that. And then once I find where its zeros are, then I will know the partition function, and I'll be able to look at it from that perspective. So Deepak's question, this is how you get the partition function. That's what we're going to do. Now, this is not a new idea. This idea was proposed by Li and Yang a long time ago, and extended upon by Fisher. Li and Yang considered the zeros as a function of complex h, and Fisher as a function of complex beta, or temperature. And they've been known for some time, and therefore studied for some time. They contain a lot of interesting information. They're telling me about discontinuities in the free energy, critical exponents. A lot of the things that you would like to get from your thermodynamics are contained in either where the zeros are, how they move with field, what their density of states is. All of these things can be gotten from the zeros. As an example, these are not the zeros themselves, but the exponential of the zeros. For the Ising model, the exponential of the zeros lie on the unit circle, which means they're purely complex. And whether you are in the magnetic phase or paramagnetic phase is given by whether they close around the real axis or not. All right, so this is a very simple example for what you can do with these. Now, these were sort of nice theoretical constructs until recently, where there was this nice paper called Experimental Observation of Li-Yang Zeros, following a proposal by Bobaway, I think, where what they did is they took this thing, now I have to look, trimethyl phosphite. They considered it as a system of spins with, I think, the central ion as a probe spin. Because what Bobaway had worked out was that you can measure the zeros if you take your system and you couple it to a probe spin in the appropriate way. And this is a nice experimental realization of that. Now, this already looks a bit like a quantum circuit, right? It looks like the stuff that I showed you guys earlier. It's not. This is entirely NMR. But we looked at this and thought, okay, well, this is certainly a thing we can do. Their measurement was great. What they did is they measured the coherence on the ancilla qubit. And thanks to the theoretical backup, what was shown is that whenever this coherence of the ancilla qubit hits 0, that's where your partition function zeros lie. And so they were able to reproduce sort of the Ising phase diagram, this thing, but for only six spins. So this is our program, and this is how we're going to measure the partition function zeros on a quantum computer. All right, so what do we need? Well, we need trace E minus beta H. Here I've written out your Hamiltonian for the Ising model. I've got the nearest neighbor coupling. I've got my C-axis field. And now I've complexified, or I've analytically continued into the complex plane by giving this an imaginary piece as well. Okay. This looks like a thermal state. Great. I already talked about how you prepare thermal states. That's the thing we can do. This looks like a time evolution operator, right? I have an e to the complex thing. You have to do a little bit more work, but basically that'll work. So there are 3 steps, 3 problems you have to do. You have to make this thermal state. We talked about that. We know how to do that. We have to accomplish time evolution. We talked a little bit about that in the context of the Heisenberg model, so we have an idea how to do that. And we know how to do this from basic quantum mechanics for density matrices. You have to pick your Hamiltonian correctly so it produces this, but we can do that. And then we have to map this onto a quantum computer. But at this point, we have all the ingredients, right? We know how to prepare thermal states. We can use a thermal field double state where you double your system, and time evolution is straightforward. Okay. So here are those represented again. Don't worry if you've never seen this much quantum circuit before. This is a box that produces my density matrix. We essentially follow the recipe from these papers, And the idea is to produce sufficient entanglement and sufficient degrees of freedom that when you trace it out, you get the state you want. This part I do time evolution, and in the same way as we collected the phases for the correlation function, we're gonna collect the time evolution phases onto this ancilla and then measure in the same way that was previous. So these are some details if you happen to know a bit about quantum computing. We found an interesting model to study. We studied the XXZ model. It has a number of phases depending on what J and JZ are. And we're going to look at this phase transition, XY, the ferromagnetic phase transition. So to give you an idea of what you're going to see, when J is small, everything is like. When J is very large, everything is XY-like. In the limiting cases, you can work out what the partition function zeros are. For the Ising case, they are entirely imaginary. There is no real components. And if you map the exponential, you get it to map onto this circle, just like we had in the pictures earlier. If you take the XY one, they look different. And what's important is that they look qualitatively different, right? The zeros in this sense do not look like the zeros in this. And this is important because I'm going to run this on a quantum computer that is really, really noisy. And I'm going to want to be able to tell the difference between this and this, right? And so if these looked the same, but just the numbers were different, that would be a lot harder task. But this will make life a little bit easier. Okay, so what we're going to do is we're going to start on this side of the phase transition. We're going to look at the zeros and then cross it and then see what they look like as a function of J by J.
Question?
Yep.
What's the temperature?
1 in this case. Sorry, 0.1. Beta of 10. So here is the results for 2 sites that took 5 qubits, right? Because I need to double my system and I need an ancilla. So this array takes quite a bit of qubits. And here's what I should get. I should get 2 zeros, 1 there and 1 there. So 2-side systems, so I don't have very many. So these are the location of my zeros that I should get. Now we tried this on the IBM quantum computers almost 3 years ago now. They essentially didn't produce anything that was useful. The new ones are much better. These days they produce something useful, but at the time they weren't. And so we contacted the group of Norbert Linke at Maryland, who was kind enough to do these experiments for us. And here's their results from their trapped ion quantum computer. Not bad, right? Especially given what I showed earlier for just a 4-site system, this is actually pretty good. This looks a lot better than it did earlier. Yes, Richard.
Sorry, what does did not produce anything useful mean? That it was too noisy, or
It was too noisy. Okay. After the length of circuit that we had to run, regardless of the temperature we ran, my density matrix was fully mixed. In other words, I had no information about my system. And then you can only run an infinite temperature case, and that's not interesting.
Thank you.
Good. So we can look at this as a function of, complex fields. As promised for the Ising model, there is no real components, but there are 2 zeros on the complex axis. Yes, Deepak.
No, so I'm just really surprised because every day we keep hearing news about the latest breakthrough in quantum computing, and what you're saying is that even at present, it's very difficult to do a computation like this for a system of how many 8 qubits you said?
I could try this for 8 qubits, but I think, so the problem is.
I mean, it's 4 qubits doubled, right?
This is 2 qubits doubled. So this is 5.
2 qubits, okay.
And it's probably, I can do that now. I couldn't do it 2 years ago. The problem is, and this goes into a little bit of detail, each of these gates has an accuracy of 92% or so. And so every time you have one of these 2-qubit gates, these controlled math gates, your accuracy goes down by 8%. inverse multiplicative, right? So like 0.92 times 0.92 times 0.92. And so you very quickly run out of anything sensible. Trapped ion gates are much more accurate, but it's difficult for them to get many more qubits. Right, so how many of these things you have in line is called your circuit depth, and so you tend to have to limit how many of those you have. So people they say, okay, well now I've entangled 53 qubits, but what they've really done is they've only applied 2 or 3 of these on each particular qubit. And their statement is correct, right? But it's a thing that works well on today's architecture. Or on today's hardware, I should say.
What about, I mean, any plans to implement a photonic version of this? I mean,
that would be nice. I have to understand how photonic quantum computers work first. So, yes, but not yet.
Okay, thanks.
Yes, Chris here.
What's the dependence on lambda on the interaction strength under your results?
Oh, I'm gonna vary it.
All right.
I haven't gotten there yet.
Thank you.
You're welcome. Okay. Right. So as promised, right, we're going to now drive this across here. We started here. Good. So this is now closer to the phase transition, right? The solid lines are still the exact results. The dots, the markers are from the experiment. You can see that the zeros move up closer towards pi/2 a little bit, right? And you can see these shift inward. Then they continue to shift inward as J approaches the phase transition. And at this point, COVID-19 happened, so we don't have any data because our colleagues couldn't get in the lab anymore. Okay. So this is on one side of the phase transition. At this point, we have a phase transition. And these are the results for beyond that. So what you can see is that these zeros, they coalesce and move along the vertical space. They acquire a real part, right? And indeed, if you try and go, for this one, we did have experimental data and they still match pretty nicely. The point is though, like you can look at these and you can qualitatively see that something has changed. So you can already tell, even on today's hardware, which is not super great, that something has gone, that you've gone through a phase transition, that you've changed the nature of your state somehow. This, of course, works for more sites. I can do this for 8 sites, not with an actual quantum computer, but with a simulator. The zeros occur still along the horizontal line here and go vertical across the phase transition, right? And so the thing that I promised that you could do is you could take these zeros and you should now, with their knowledge, be able to reconstruct a partition function and from that, whatever you want. We chose to look at, in particular, the log of Z, so the free energy. And here are the results. The blue line is exact. These come from simulator where I didn't have data, and these are the data points from the trapped ion quantum computer. The error bars are smaller than these markers. So this is quite good. Right, this is a very nice agreement from a current era quantum computer to what we know the exact free energy is, and for something that's relatively difficult to measure. So we were pretty happy about that. Okay. So I have another section. It looks like I have about 15 minutes. Adrian, Kasia, do you want me to go or wait for questions, or how would you like to do this? Continue. This one is much shorter, so this will help.
Go ahead. Yeah, I would say
good.
Continue.
So very briefly, we are all mostly aware probably of how topology has changed how we think about physics these days. The very first example of this was in 1980, or what we now know is a reflection of topological physics in the anomalous quantum Hall effect. One of the things we know about topological states is they are supposed to be robust. What does that mean? Meaning that if I have some system that has topological edge states, I'm supposed to be preventing backscattering, right? So these, because they're physically separated, I cannot mix these two, and so I have protected transport. From an energy for dispersion perspective, I have nice, well-separated bands that don't mix with anything else, and so they tend to be protected from all sorts of disorder, all sorts of other things that I could do with it. So naturally, people have tried to measure this on quantum computers with the idea that a measurement or a quantity that is insensitive to noise would be really great to try and measure on a quantum computer, which is really, really noisy. No? So these are some attempts. I'm not going to expect you to understand what all of these things are, but so these folks looked at Floquet topological states. In particular, they tried to look for boundary states, edge states. The problem there is that your system is not really big enough, and so your boundary states mix, and so it's still not as protected as you'd like. This is from our group. We measured the entanglement entropy of the Kitaev honeycomb model. These both have downsides. You need a classical comparison to know what the state is. You can't tell whether the true number is 1 or -1, and you just know that there is one. This work was done with a 1D topological quantum walk. You can kind of see where a topological phase appears in their paper, but it doesn't generalize very well. This is a nice paper on symmetry protected topological states. It's also limited because it works for short range entanglement only. And is still relatively noisy. So we asked ourselves, can I do something general that was applicable all over the place, where I can measure a topological invariant, even for long range things? And the answer is yes, by leveraging holonomy. So the idea is as follows. Holonomy tends to come up in the context of curved spaces, right? And parallel transport. It's how much does your vector move on my space as I undergo some closed path. Now for quantum mechanics, right, when I'm not looking at some vector in 3 space under general relativity, what my vector is my wave function vector. It lives on a torus, it lives on the 2D periodic manifold. And to give you an idea what this looks like, here is a simple model that has a topological phase. The trivial phase, all of the wave functions here represented as pseudospins, all point up effectively, right? And for the topological non-trivial phase, they go up and they go down and then they come back to being up. So this is where this idea comes from of your wave function twisting as you go across your manifold. This is essentially what that's supposed to mean. So the idea is, can we take this idea and see if my wave function gets twisted as I go around in momentum space? Let's see if we can measure this on the quantum computer. It turns out generally this is hard. There is a really, really nice paper by Fukui in JPSJ that for any numerical person that wants to compute Berry curvature and Chern number, this is the method you want to use whether you're doing quantum computing or not. It is really, really well done. Effectively, what you do is you measure local fluxes and you sum those up. But another perspective on that is you essentially measure the overlap between one point on your manifold, your momentum space, and then the neighboring one. So if I take my manifold, my momentum space, and I discretize it, and I pick some point theta and a point theta plus delta theta, I just need to look at the wave function overlap between those. From a quantum computer, the way you would do that is you prepare your wave function theta, you evolve it to theta plus delta theta, and just like before, you measure the phase when you do that, right? And that is how you measure a wave function overlap. So that's what we did. So we took that and we took a path along the Brillouin zone. In a non-trivial phase, right, the phases that I pick up eventually should wrap around. So this is for the non-trivial phase. It starts from 0, it goes up, and then because this is like an arctangent, it comes back down from the bottom. In the trivial phase, everything is always pointing up, and so I never have this option of wrapping around my manifold. It doesn't happen. The blue lines are exact. The dots and lines are from the IBM Toronto, one of the quantum computers. And you can kind of see it works a little bit, right? These at least are qualitatively different from these. For the trivial phase, each line is one experiment. So we can run this multiple times and sort of see what we get. These don't really shoot up or down. They sort of nicely stay within their box, whereas these have all of a sudden a sharp jump that you could think of as, okay, this is because I've run across the edge of my manifold and gone back to the other side. Yes.
How big is the system?
This is 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is 10 by 10 discretized. Good. So this is one, and you can kind of see it, and it kind of works, but it's not great. The method that was introduced by Fukui is to do something else. They say what you should do instead is you should compute the flux through each patch, and then for each patch, see if you move off the principal branch of your logarithm or not. So what that looks like from a quantum computer, because it's noisy, is I might get, I might shift off my principal branch either upward or downward. And that can happen at any given point, depending on what the noise in my machine is and whatever else is going on. But the total sum of them will give you either 0 or 1 or 2 or -1 or -2, and that sum is your Chern number. So you can tell in trivial case, every white one is negative and every black one is positive, right? We have 1, 2, 3, 4, 5, 6 negative ones. 2, 3, 4, 5, 6, 7. Oh, I've inverted them, I think. So this is the non-trivial phase, and this is the trivial phase, right? The total number adds up. And what happens is when your quantum computer, say, introduces some other noise, it might make this one here positive, but the neighboring one has to go negative because I have conservation of flux. And so in this way, you always end up with some integer number. So this is what we ran. We measured the Chern number on the quantum computer. These are the red circles. The black line is what you're supposed to get as an exact answer, and sure enough, these match perfectly, even close to the phase transition. You can look at this, and this is the first time that we are aware of that anybody's pulled an error-free measurement from a quantum computer. Right, there are no error bars because I either get 1 or I get 0 or I get -1. Eventually, of course, things have to get too noisy and it won't work anymore. So we did some analysis and figured out, how many times when you run this do you get it wrong? And what we did is in the simulator, increase the gate error. And once you get below a certain gate error of 8% for single qubit rotations, everything is perfect. Above that, you start to have some mistakes where this doesn't work perfectly anymore. And so if you run it 1,000,000 times, you'll get a bunch of numbers down here, but some of them live up here and some of them live up here. Yeah, so this is a way of getting at topological physics, even on today's quantum hardware. And with that, I think we'll stop. We've been having a lot of fun looking at condensed matter physics problems on quantum computers. This is just 2 of the things that we've looked at, but I think they're promising. And I think, we can also learn something going the other way. From things that you've executed on a quantum computer, you can go and say, okay, well, this is a nice idea. How can I use this on my classical calculations? And at least on one occasion, this has been shown to be more useful on the classical machine, not for us, some other people's work. So it's things to keep in mind, even if you don't do quantum. All right, that's it. Thank you.
Thank you very much. Very nice talk. Questions? We have time for questions. Deepak.
Yeah, hi, Lex. This was a very, very nice talk. My question is about the topological measurement. What is your, when you say, what does your quantum circuit look like? How many qubits are there and so on and so forth?
Good. So for this particular model, so we're looking at, this is, it is it's a 2-dimensional PF superconductor. It's not so relevant what it is. It factorizes in momentum space. Actually, so hold on. I have the precise circuit for you. If you give me a second, I can dig that out. Once I find it. Hold on. I have too many slides. Aha. So this is what it actually looks like. or at least this is what one of the things looks like. So effectively, we know for this particular model precisely how to diagonalize the Hamiltonian. And so we've essentially gate-wise implemented what we know classically our diagonalization to be. You can work that out on pen and paper. And so this is just a controlled 2-qubit rotation. It looks messy because everything that is more than 2 qubits is messy. But this is a controlled 2-qubit rotation where I just rotate it so I know what the correct wave function to be. We've since extended this work, and we also have a variational way of doing that. This is the basic idea.
I guess my question was like, what is the size of the system? Is it still a 2-qubit system that you're looking at?
So because it factorizes in momentum space, it is a 3-qubit calculation, one for each band. Those are my 2 systems, and one for the ancilla to keep track of the phases.
Okay.
So that's because it factorizes nicely in momentum space in this case.
Okay. Thanks.
I have a question. This is Noah Brayali. Hey, Lex, great talk.
Thank you.
You mentioned that 2-qubit error rates are something like 92% on the fidelity 92%, 80% error rate, and that was thinking about the flux qubits. And you just mentioned a moment ago this threshold of 8% error rate for the single qubit.
Yeah.
And so I was wondering if we could try and put the apples and oranges together. So for the flux and the ion computer, what's the kind of quality factor? How many, what's the ratio of the single qubit error rate to the 2-qubit error rate for those 2 machines?
So for this one, this is on the superconducting qubits. The 2-qubit error rate is roughly 10 times the single qubit error rate. Right, the single qubit here is 0.8%, and we know that they're roughly 8%. For the trapped ion machines, I don't know. They're looking at, for single qubits, or I think for 2-qubit error rates, looking at 99% fidelity. But I don't know for certain. I would have to check precisely with what they've got.
And for ions, the single qubits?
Much lower than that.
And the ratio?
Low enough that I don't care. I mean, this is
more than
sort of a flippant statement, but it is generally true that like your error is going to be dominated by whatever your 2-qubit gate error is. Right, and so essentially you can. And since they're usually an order of magnitude apart, you can treat your single qubit rotations as effectively free. And what's limiting your error is your 2-qubit rotations.
So you think it's about the same? The quality factor, the number of single qubits you can do before there's a 2-qubit error is about 10 for both the ion and IBM flux.
I don't know. I actually don't know what they are for
the ion.
For the ion,
it's definitely it's 10 for the IBM machine.
It's 10 for the IBM machine.
That's beautiful. Thank you.
I'm sure IonQ has it on their website.
Let's call for questions. If not, let's thank Lex again. Thank you very much for this exciting talk, and hope to see you all next week.
Thank you all for having me. I had fun. Thank you for good questions.
Thank you, Lex. Goodbye, everyone.